Hi there, everybody. I'm attempting to make this video during a thunderstorm, so we'll see how this goes. So we're going to do section 2.3, and 2.3 is a continuation of the previous section. So 2.2 and 2.3 are really like one big section just chopped in half. So we're going to keep going with a lot of the stuff that we've talked about so far. So we're still doing quantitative variables. We learned about the mean and the median, and now we're going to learn about what we call spread, which is variability. So the first example here is dealing with Washington, D.C. and San Francisco in the United States. Turns out they have the same average annual temperature, which is 58.2 degrees. So when we discuss a quantitative variable, in this case like temperature, that's only one way to describe the data, right? But quantitative data has variability. And so we have to describe the variability using, some kind of measure or calculated statistic, as we'll see. So the open question at the bottom, so the cities have the same average annual temperature. Do they have the same average temperatures during every month? So before we go to the next slide, just think about it. So in the summer, think about Washington, D.C., right? So it's pretty close to us, as you can see here, right? So the weather's going to be like us. It's a little bit hotter. So it gets pretty hot. San Francisco, does it get hot there? Right? It turns out it doesn't. It never gets above 85 degrees probably in San Francisco. What about in the winter? Well, Washington, D.C., again, similar weather to here. It snows there and things like that. What about San Francisco? Does it snow in San Francisco? It turns out that it doesn't. San Francisco never gets colder than about 40 degrees. So it turns out that during most months, San Francisco and Washington, D.C. have very different average temperatures. But you can see that in the spring and in the fall, they have similar temperatures. But most of the other parts of the year, they have different temperatures. So you can see throughout, just looking at the data here, throughout the year, San Francisco is very consistent, right? The average temperature in January is not too much different than it is in July. That's might be surprising to some of you. It's just very consistent weather. What about Washington, D.C.? It gets very cold in the winter, very hot in the summer, just like it does here. So because San Francisco is more consistent, there is less variation in temperature. So variation mathematically is the opposite of consistency. It just means that the data values move around a lot, or they're hard to pin down, or they take on a lot of different values, anything like that. So we're going to have three ways to measure variability. All of them are important. All of them do different things. So I'm just introducing the ideas here, the terminology here. First thing is a standard deviation. It turns out that that's going to have the notation either S or the Greek lowercase letter sigma. More on that later. I'm just introducing it here. Something called the range, and then something called the interquartile range, which we just call the IQR. Because both of these two have the word range in them, just call this one the IQR, so you don't mix up which one is the range and which one is the interquartile range. So for all of these measures, a larger value of the statistic corresponds to more variation in the data. So that's what we want. When we come up with a variability measurement, we want a bigger number to mean more variability, right? That makes sense. And these values always must be positive numbers or zero. So none of these variabilities are allowed to be negative, because these are all related to distances, and distances are always positive. They're distances on the number line. So now what we're going to do is we're going to do something a little bit different than what we've done in the past. and we're going to just compute a whole bunch of stuff on the calculator. So the way you do this, so I'm just going to follow the directions here, so just watch me. You're going to have to do this a whole bunch. Not so much in this section, but definitely in the next few sections, we're going to do a lot of calculator work, and this is one of many ways. So turn your calculator on, and then to enter the data, go to Stat Edit 1, okay? So here's the Stat button. Here's Edit, so my calculator defaults to this setting, so I just hit Enter. Notice that I have some values there already. Now, look at what it says here. Clear any old data values in L1 if necessary. Use the arrow keys to select L1 and press Clear. So here's the arrow keys, right? I can move around and stuff. I'm going to go all the way up to L1, and then I'm going to hit Clear, and then Enter, okay? Do not hit Delete, okay? Clear and delete are not the same thing. Now that I've cleared out the data values, you don't have to clear them out. You're allowed to write over them, but sometimes there's extra numbers left in the bottom, so just to make sure you clear out all the extra numbers, because you can't really see the ones that are like down here. Enter new data values as a vertical list. So, all right, so 1, enter, 3, enter, 4, enter, 5, enter, 7, enter, 10. You guys get the idea here. Oh, that was weird. And then go back through and make sure that they actually went in correctly. 20, 25, 31, 42. Yeah, so you can scroll up and down with your arrow keys. Just make sure you entered it correctly, because once the numbers are in here, you don't really have any control over what they do. Okay. Then what you do, to compute the summary statistics, go to Stat, go over here to Calc, just right arrow over to Calc, and we're going to do one variable stats and just hit Enter. Just hit Enter a couple times. It'll know what to do. If for some reason this list is not your current list, the L's are here above. So if you wanted to type in, I'm not saying you should do this, but if you wanted to, let's say you put your data in L2, list 2, go to second 2, and it'll type L2. All of the calculators that you're using, you probably haven't been used before to do this stuff, so they're probably defaulting to L1. If it doesn't say L1 here, second 1, we'll put L1. Frequency list, don't worry about it. Just skip it. Just keep hitting Enter. Just keep hitting Enter until a bunch of stuff happens. That's what's going to be on this list here. Okay, so use the arrow keys to scroll through your results. So make sure that the numbers on your screen look like these numbers. If they don't, go back and do the part we just did again. All right, and then you just scroll up and down, right? Okay. So some of these statistics you will recognize. The ones I put in blue here, if you're colorblind, I apologize in advance, but not much I can do with PowerPoint. So you can see X bar. We've seen X bar before. That's our sample mean. Your calculator treats this as a sample. Even if you're typing in data from a population, your calculator will treat this as a sample. So it's going to call this X bar, not mu. Then we have sum of X. We saw that notation last video. That just sums all the X values. Then we have N, that's our sample size. So there's 11 data values. And then the median is 10. So that's down here, right? Median is 10, right? Now, the ones in green are the ones we're going to learn about in this section. So the first one is this SX. The subscript here, oh yeah. So this X is a subscript. It just means S. So S is what we're going to define as the standard deviation, which we have not defined yet, but we will. And then this little guy is sigma. Whenever you type in data, you're just going to use S. So sigma is a thing that is used. We're not going to use it, okay? But we will learn about it in this section. But we don't use it to solve any problems. We only use S to solve problems. And then we're going to learn about these other green ones. And then one of them we don't use at all. This sum of x squared, we don't use this. So you don't need to worry about it. So on the homework, if your homework says, compute the standard deviation of this data set, you will type it in using this method, and you will read S as your standard deviation, not sigma. And we'll use this to do some other stuff later. So here's what the standard deviation is. So that's the most important things here, this S and this sigma. The standard deviation of a sample or a population gives a rough estimate of the typical distance of a data value from the mean. This is not the definition, this is just what we use it for. The definition is on the next slide. So the sample standard deviation is S. It measures how spread out the data are from the sample mean x bar. And the population standard deviation is that Greek lowercase sigma, and measures out how spread the data are from the population mean mu. So if you're given a sample and have to compute S and x bar, you're just going to use this method. You're just going to type it into your calculator and have the calculator do it for you. If anybody out there watching the video has ever computed a standard deviation by hand, you know how, I'm not going to call it awful, but it's tedious. Let's just say that. It's very tedious. And so we don't want to sit around doing tedious calculations in this class. We'd rather have technology do the work, and then we can start to interpret results and actually get work done, which is more interesting. All right, yeah, so that's pretty much what we're going to use this for, x bar and S. Here's the definition. So this formula is the definition, and it's, again, very tedious to compute this by hand. I will not do it. You don't have to do it. But if you're really interested and want to see this at work, you can. There are examples in the book that you can look at, but I'm skipping them. I'm not assigning them. So look here. Look at what it says. You take every data value, subtract x bar. So if we were talking about this that we just calculated here, you would take every data value that you typed in, 1, 3, 4, 5, all those data values we typed in, subtract the mean, square each of those differences, sum all those squares, divide by n minus 1, n is 11, so you would divide by 10 and then take the square root. That's where this number comes from. So if you want to do it by hand, I'm not going to stop you, but I'm also not going to assign it. You will not need to do it. So let's get work done. It's much more interesting to see what this standard deviation does. So here is the data for the mean and standard deviation for the daily high temperatures of Washington, D.C. and San Francisco in April 2018. So I just picked this month at random. I just looked up the data. I wanted to pick a month where the means would be fairly close. And I expected that Washington, D.C. would have more variation because the temperature fluctuates more. More hot days, more cold days. And that's exactly what happened. So here, so in April, there's 30 days. So there's 30 dots in this dot plot, 30 dots in this dot plot. And you can see what's going on, right? Washington, D.C.'s high temperature is all over the place in April 2018. San Francisco's is a lot more consistent. Again, it gets pretty hot. You know, it got 86 degrees one day, you know, or 85 degrees one day, which is very, very hot for San Francisco. But it didn't get as cold. So there's more consistency here, less variability. That's how it works. And that's reflected in this standard deviation measurement. So it doesn't matter what the mean is. What matters is this S. So what this is saying is that this is about how much variability you would expect to see. And we're going to have a more locked down version of this variability in a second. But for right now, just imagine it's basically saying that most of the data is going to be within one standard deviation of the mean. And that's what happened, right? So the mean here is 62.8, which is right about here. And if you go out like 10 on each side, that's from like here to like here, you get this range right like that. That's most of the numbers. And that's how it works. So again, it's like a typical amount of variation in the data. San Francisco, S is smaller, there's less variation. And you can see that there's less variation in the dot plots. So the two go together, right? If the dots are more tightly clustered together, S will be smaller. If the dots are more spread out, S will be bigger. It's that simple. And that's all you have to use it for. You don't have to compute this number by hand. You're only going to use it as a comparison tool, and you're going to use it to do the things later in this section. So we're basically just dealing with S the rest of the section. So now we have something called the 95% rule. And this is the main rule that we use in this class that involves the mean of the distribution and the standard deviation. Whenever those two numbers are presented together, this is probably the rule we're going to use. So if a distribution of data is bell-shaped, about 95% of the data should fall within two standard deviations of the mean. So what that's saying is that it is predictable in a bell-shaped curve that if you try to identify where the middle 95% of the stuff is, if you're talking about dot plots, where's the middle 95% of the dots? If you're talking about a histogram, where's the middle 95% of the bars? Doesn't matter what graph you're using. You just estimate where the middle 95% is, and the boundaries of that 95% will be x bar minus 2s and x bar plus 2s. And that's what this is saying, right? Approximately 95% of the data from a bell-shaped distribution should fall in that interval. So a couple things that mess students up, that we're going to use this 95% rule a lot, so you need to know it, is that the numbers it's referring to are the numbers here on the number line. Remember, this is just a stand-in for a dot plot or a histogram. The height is the frequency, right? So it's how many observations are in that category or that range of values. So when we say 95% of the data, we're not talking about on the number line. We're talking about everything under the curve, right? But when we talk about x bar plus 2s and x bar minus 2s, those are numbers on the number line. Those are the markers at the bottom. All right, so let's use this 95% rule to get some work done. So we're going to use the 95% rule to find an interval that is expected to contain about 95% of the data values. Which values would be considered unusual? So a bell-shaped distribution with a mean of 250 and a standard deviation 26. Let's do that one first. So so go back and look at this and imagine that our mean is 250. So it's some sort of measurement, right? $250, to purchase a, mountain bike or something. And the standard deviation is $26, right? So 95% of mountain bikes cost within this interval, so it would be like 250 minus 2 times 26 and 250 plus 2 times 26. Right, so we need to find that interval. So x bar is the mean, s is the standard deviation. Just plug everything in. right? And just do it on your calculator. You can type it in exactly how it looks, right? 250 minus 2, and you don't even have to type times. You can just use parentheses. You can type it in exactly the way it looks. Your calculator knows what to do. Right? So type it in exactly the way it looks. So that means 95% of mountain bikes are between $198 and $302. 95%. That's a good rule. So which ones are unusual? Well, the unusual bikes would be outside of that range. So think about what it's saying, that the 95% rule captures 95% of the data values. Those are considered not unusual, right? Or common or expected. Anything outside of that range, anything we call the tails of the distribution, anything in the tails is considered unusual. So if we're doing mountain bikes or whatever example you want to think up for this, anything less than 198 is unusually low, and anything above 302 is unusually high. And we can go back and look at that graph again, right? Here's 250. Here's 250 plus 2 times 26. Right, so here's 302, here's 198, and you can see 95% of the prices will be in that range. So anything in the tails, is considered unusual. What about part B here? Mean 0, standard deviation 1. Well, it's the same thing. We need to find the interval. So we just did this one. So it's 0 minus 2 times 1 is negative 2, and 0 plus 2 times 1 is 2. So any values outside the interval negative 2 to 2 are considered unusual. So a couple of things I want to point out. X bar is allowed to be any number, right? Because you could be measuring temperature at the North Pole. It's going to be negative, right, in Fahrenheit. S is like a distance measurement, so it's not allowed to be negative. But whenever you add or subtract numbers, and one of them is allowed to be negative and one of them needs to be positive or 0, you can have negative numbers in your answer. And that's what happens sometimes. So don't worry about negative numbers in your answer. That's totally fine. Just try to invent a scenario that, the numbers you see fit that data. And just imagine, so if this is some kind of temperature measurement or something, of course it can be negative. Some students get really bent out of shape about negative numbers, and I don't want that to happen to you. S is not allowed to be negative, and other numbers in the class are not allowed to be negative. But things like this, it's totally fine. All right, so let's go backwards. What if we're given a bell-shaped graph, and we have to estimate X bar and S? So we went forward in the last problem. How do we do it going the other direction? All right, so where is the mean of this distribution? So think back to what we did at the end of the last section. For a symmetric graph, the mean and median are the same, and the median is the middle. So X bar is just the center of the graph. It's going to be 500, right? It's going to be right here. Next, you have to figure out where 95% of the data is. So to me, it looked like 95% of the data is between 460 and 540. It does take a little bit of practice to be able to find where that 95% is. But that's what it looked like to me. Now, we know that the boundaries of that 95% are X bar minus 2S and X bar plus 2S. We already know X bar because we found it in up top. So we have to use a little bit of algebra. This is the only algebra we pretty much use for the first 4 to 5 weeks of this semester. So what I'm going to do is you have to just solve for one of the endpoints. You don't have to do both, just one. I just picked X bar plus 2S is 540. So notice here, we know that this is the upper boundary of the 95% rule. We know it's equal to this. So we just set those equal to each other. Then we know x bar is 500, and then you just use algebra and solve for s. So it turns out s is 20. So not very much algebra. You're just solving for a variable. So shouldn't be too bad for you guys. I do want to point out that there are other ways to find s. You're allowed to use any way you want. You just have to show some work. Just don't, you can't guess on problems like this. So if you're watching videos that other people have made, like videos from the textbook or whatever, there's more than one way to do this. So don't think that just because you saw a different method that you have to use that method. You're allowed to use whatever works for you, okay? To me, this is the easiest way to do it, but if you can find another way, I'm sure it's totally fine, as long as you're getting the right answer and you can show the work. Oh, and then I circled the answers in blue. All right, next up, we're going to talk about something called z-scores. So z-scores are like an extended version of the 95% rule. And we're going to start with an example just so you kind of get the idea what's going on here. So suppose Brian's monthly smartphone data use is bell-shaped with a mean of 13 gigabytes and a standard deviation of 3 gigabytes. So let's say you have a sample of his monthly smartphone bills for the last year or so, and on average he uses about 13 gigs of data, and let's say its standard deviation is around 3 gigs. Well, last month Brian used 6 gigabytes. Is this an unusual value for his monthly data use? So this is a very common question in statistics. Based on past data, is a particular observation or data value unusual? So to answer a question like this, we use a statistic called a z-score, which counts how many standard deviations from the mean that a given data value falls. You are also allowed to use the 95% rule. But we actually get more information from a z-score. And the way you compute a z-score, so if you have a data value, so the data value is always x, just the variable, from a sample with mean x bar and standard deviation s, the z-score is data value minus the mean divided by the standard deviation. For a population, we replace the sample mean with the population mean and the sample deviation, standard deviation with the population standard deviation. So z-scores work for samples or populations. Generally speaking, at least early on, we just work with samples. The z-score tells how many standard deviations the data value is from the mean. Positive z-scores are above the mean. Negative z-scores are below the mean. So again, here's another thing that's allowed to be negative, right? This is allowed to be negative. This is allowed to be negative. This isn't, but if you're dividing by a positive number, then whatever happens here, it either stays positive or stays negative. Or this could be 0. So on the homework and on a test, you're going to have information about z-scores. If your x is to the right of x bar, positive z-score. If your x is to the left, negative z-score. So this is what happens if we compute the z-score for Brian's 6 gigabytes of smartphone data usage. So his data value was 6. Right, 6 gigabytes minus his mean, his over the last year or so was 13, standard deviation of 3. You get negative 2.33. So this means 6 gigabytes of data is 2.33 standard deviations below the mean. So just think about what that's saying, right? It's saying that this 6 gigabytes is very far to the left of that bell-shaped curve. Does that make it unusual? Well, it turns out that it does. We know that 95% of values should fall between x bar minus 2s and x bar plus 2s. Values with z-scores above z equals 2 or below z equals minus 2 are considered unusual. So here I just made a chart of the z-scores and superimposed it on top of our 95% rule. And you can see that everything lines up. So when you have your 95% rule is, x bar minus 2s, that was here. So see the minus 2? That's this minus 2 right here. And, x bar plus 2s, well, that's this 2 right here. So all I did was I just, built this. So I said this is x bar plus 0s. So I just wrote the 0 down. So the z-scores correspond to adding s or subtracting s as you move away from the mean. And so the unusual values are in the tails of the distribution, anything to the right of here and anything to the left of here. So when you guys are doing problems on the homework or a test that look like this, just remember, if your first instinct is to just calculate, that might not be the best way to approach it, okay? Many of the problems on the homework are designed just to get you to use these rules and, not necessarily calculate a bunch of stuff, but just use the rules to draw a fast conclusion. So if I tell you a z-score is negative 2.33, just think where it would be on this graph, right? Negative 2.33, so this is Brian's 6 gigabytes of data usage, is over in this region. Well, that's pretty far into the tail of the distribution, so it's unusual. It's less than negative 2. And that's how it works. Moving on. Oh, there's my shading. Yeah, and so you can see, there's your 95% rule. All right, so now we're going to use z-scores to do something else. We just saw how to use a z-score to determine if an observation is unusual. And we can see that that method lines up with the 95% rule. Let's use the z-scores to do something else now. So Amanda took 2 standardized tests before she applied to colleges. She scored 1250 on the SAT and 27 on the ACT. So here's the summary statistics for all students taking these tests given in the table. So everybody that took these tests, I just called it a population mean and a population standard deviation. I mean, technically it could be a really big sample, but let's just call it the population. This is for all students. The mean for the SAT is 1050. The standard deviation is 194 for exam scores. The ACT is 20.8 with a standard deviation of 4.8. So if Amanda can only submit 1 test score on her applications, which result is more impressive? So the idea is that Amanda scored really well on the SAT and the ACT, but which one is going to look better to a college entrance judge, somebody that determines whether the student is capable of going to that school? So the way to do this is z-scores. So the z-score for the SAT, so it's the observation minus the mean divided by the standard deviation. Z-scores are almost always rounded to 2 decimal places. So Amanda scored 1.03 standard deviations above the mean for her SAT, which is very good. What about her ACT? Data value minus the mean divided by the standard deviation. She scored 1.29 standard deviations above the mean for her ACT. So her ACT score is actually better compared to everyone else who took it. So it's not enough just to subtract the 2 numbers. You have to subtract the 2 numbers and then scale it by the standard deviation of the population or the sample if you're doing samples. Here it's a population. And the ACT score was better because it had a higher z-score. If you're trying to determine if somebody's a better golfer, low z-scores would be better because a low golf score is better. So these numbers translate directly into whatever it is you're trying to evaluate. Here, higher scores are better, so higher z-scores are also better. So how do we compare the data values in other ways? So we saw that Amanda scored well above the median on both of her standardized tests. So we know she scored better than more than half of the students who have taken them. One quick note, anytime in the PowerPoints I put in little hints like this, that means that's something you should think about, that if you don't know why this is true, you should really think about this or ask somebody about this. Okay, so I kind of put little like mini quizzes in there, so make sure you understand how we are aware that Amanda scored better than the median on both of her tests. Because the median is not involved in any of these calculations, right? The mean is in these calculations, but just think about that. So let's say Charlie scores exactly the median on the SAT. Then he has half of the other scores below his and half above. Let's say Charlie is a perfectly average student, scores exactly the median. So 50% of scores are below Charlie's, and we say that his score puts him in the 50th percentile. Whenever you take a standardized test, the results, when you get them back, compare your score to the score of everybody else who took the test. And it's often shown as a percentile. Or if you have any kids and that you saw them taking standardized tests in school, you see that there are percentiles. Well, a percentile is just the number, the data value, where P% of the data is below that number. And this is shortened to percentile, or just the percent sign with the word tile. And it's just a cutoff point. It's a boundary. So Amanda scored in the 90th percentile on the ACT because 90% of students scored lower than she did. So her value, her ACT score, 27, is the 90th percentile. So everybody that scored a 27 is in the 90th percentile. That just means they scored better than 90% of students who took the test. That's it. And don't forget that this definition is pretty technical. The percentile is the data value. So this is the percentile, not this, right? So if I say what's the 90th percentile for such and such, it's the data value where 90% is below. And in example 2, we computed the summary statistics for a data set, right? So let me go ahead and call it back up here. Right, so you already have it in your calculator. So the last four numbers, 1, 4, 10, 25, 42, these are called the 5-number summary. So this is the minimum value, Q1, this is called the first quartile, the median, third quartile, and the maximum value. We've already studied the median, so you know what that is. But we need to talk about these other things, right? So the minimum value is pretty clear. That's the smallest number in the data set. The maximum value, that should also be fairly clear. Biggest number in the data set. What are these quartiles, though? Let's talk about quartiles. Oops. So about 25% of the data values fall between any two consecutive numbers in the 5-number summary. The 5-number summary can be used with any distribution shape. So I accidentally cleared this out. Let me put it back. So what this is saying is that, as you recall, when we typed these numbers in, there were 11 numbers we typed in. And it went 1, 3, 4, 5. So the idea here is that the 5-number summary breaks the data set into 4 equal-sized regions. And it doesn't matter what the shape of the distribution is, it'll work. So the way this is done by hand, we know how to compute a median by hand. What you would do is, after you compute the median, you would go back and, let's look at the picture, it's probably easier. So Q2 is the median, second quartile, so 50th percentile. Right, first quartile, 25th percentile, 50th percentile, 75th percentile. That's where these Qs come from, because it's like first quarter is 25, second quarter is 50, right? Percent. The idea here is after you find the median, you can go back and look at what's remaining and find the median of that lower half. That's the first quartile. And then you could find the median of the upper half. That's your third quartile. So it's like one median and then two medians of the remaining 50%, which splits it into 4 equal-sized parts. Right, and I obviously just showed you this. And you can see visually here sort of what's going on. That these are, now this is a small data set, 11 points. You can see that these are roughly equal-sized, right? That this splits the data into roughly equal-sized pieces. There's one number here, 2, 2, and 1. The 5-number summary can never split the data in such a way that there'd be like 1 here and 3 here. It just can't happen because of the way medians work. And the 5-number summary gives us a picture of the data. So, for example, just looking at this, would you say this is symmetric, skewed left, or skewed right? This data here. If you're not sure, pause the video. All right. So, in order to determine skew, we need to know the mean and the median, right? But let's say you're not given the mean. Well, which of these is more likely to be an outlier? Do you think 1 is an outlier or this 42? Which one do you think is farther away from most of the data values? Well, look how far it is from the median. 1 is only 9 units away from 10. 42 is 32 units away from 10. This is more likely to be an outlier because it's farther away from the center. So this distribution would be skewed to the right. So you can use the 5-number summary to determine skew and to sort of estimate where the outliers might be. And of course, there is something I need to talk about, and it's that StatKey and the graphing calculators don't agree on how to compute percentiles. You don't need to use any StatKey in this section, but you will in the next section. And so just remember that if you're using StatKey to compute quartiles, StatKey does not include the maximum and minimum values in the calculations of the quartiles. For the 5-number summary in example 2, StatKey gives us this here. And you will need to use StatKey to complete any online homework or adaptive practice quizzes that use percentiles, quartiles, or 5-number summary. That comes up a little more in the next section than in this section, but if you see a homework problem that says compute a 5-number summary, compute quartiles, just go ahead and use StatKey just in case. I'm going to put a little StatKey at the end of this video if it's not too long. If not, I'll start the next video with it. So here's using the 5-number summary. For the SAT, the 5-number summary of all test takers is, here's your 5-number summary, 400, 910, 1050, 1190, 1600. What percent of test takers scored between 910 and 1190? So just go back to the picture again, right? So 25% scored in between these two, 25% in between these two. So every consecutive number in the 5-number summary, or consecutive numbers, has 25% of the data. So if it's 25% here and 25% here, then that's 50%. Right? So 50% of test takers scored between 910 and 1190. Estimate the 60th percentile. Well, we don't know how to compute the 60th percentile. We never learn how to compute that. Instead, we're going to estimate it. So where is the 60th percentile? Well, here's the 50th, and here's the 75th. So it's somewhere between 1050 and 1190. And it's probably close to the middle of that interval, because 60 is close to the middle of 50 and 75. So there's your answers. So don't worry about this kind of stuff. You have to estimate things on the homework. Any number that's close is fine. If it's on a test and it's multiple choice, just guess the closest number and you'll be fine. And that's what we use quartiles for. It's just estimating, just getting a general idea about what's going on. All right, last two measures of spread, the range and IQR. So the range is just the maximum minus the minimum. It summarizes the full extent of the variability. It is not resistant to outliers. You can see why it would not be resistant, because if there are outliers, one of the outliers might be the maximum and one might be the minimum, so the range basically is very non-resistant. It's easily influenced by outliers. The second formula here, the IQR, is actually the middle 50% of the data. It is resistant to outliers because outliers are at the edge and Q1 and Q3 are towards the center. So now we have three measures of variability: standard deviation, range, and IQR. They all have their own uses. And ordinarily, we compute the 5-number summary using technology, then compute the range and IQR by hand, which is what we're going to do. And that's why this mostly shows up in the next section, where you have to use the IQR to solve problems. So verify that the range and IQR for dataset in example 2 are these two numbers, right? This thing keeps turning itself off, but let me put them back up here again. Right, so the range is the largest number minus the smallest. So 42 minus 1 is 41. And the IQR is Q3 minus Q1. So Q3, Q1, 25 minus 4 is 21. Now that's using the calculator. If you were to do this in StatKey, you might get a different number because StatKey computes quartiles using a different process. But I'm just showing you just with the calculator. Everything on a test is calculator only. Please do not use StatKey on a test. All right, so how do we choose what to use to describe a data set? So the mean and standard deviation are often paired when summarizing a data set. Both the mean and standard deviation have the advantage that they use all the data values. So that's good. We want our summaries to represent our data properly. So you'd want to use all the data values. But they're not resistant to outliers, so you have to be careful. If outliers are present, you don't want to use the mean and standard deviation. The median and IQR are often paired when summarizing a data set. Both are resistant, so that is a plus. But again, they're considered to be less useful because they don't fully represent all of the data. Right? The median and IQR, the calculation for finding them uses at most 6 data values, which is not that many. If there are outliers or the data are heavily skewed, the 5-number summary can give more information, such as direction of skewness, than the mean and standard deviation. And we saw that here, right? We saw that this is skewed right because this 42 is farther away from the median. So the 5-number summary is very useful. In general, sort of like in the real world stats, all of these are used, and anyone trying to learn from data tries to learn something about the data set from any measurement, and by comparing measurements to each other. All right, well, that's the end of this section. There's your summary stuff. And if you need extra practice, there you go. All right, let's see how long this video is. All right, we're at 49 minutes. I'm going to stop. I will show you guys the stat key in the next video. All right, you guys have a good day, and I will see you next video. Bye-bye now.